Good. Thank you for attending the session and sticking around. I'll be speaking about our paper on determinantal expressions for certain integrals on symmetric spaces. This is joint work with Dr. Salem Said, who's CNRS at the University of Grenoble. And this work really started in the context of some other collaborations I had with Salem, and we sort of noticed certain nice expressions and patterns in certain integrals. And then he really ran with the idea and worked out a lot of the technical details behind this work. So he's been really the driving force, but unfortunately he couldn't be here today. So I'll be taking over and trying to give a sort of overview of the topic and a sense of where it's going. And I would also like to sort of emphasize a bit the motivation and background more than maybe some of the details. This is sort of preliminary work. It's sort of the first step in what we think will be a research program in the next coming years. And there'll be a long, detailed journal paper coming out in a few weeks. So this started with the question of how can we compute integrals of the form at the top of the slide there, where you have essentially here we were interested in integrating the exponential of minus d squared over some Riemannian symmetric space of non-compact type. And the aim of this paper and the talk is somewhat modest, as I said. The aim is to show that the integral of a k-invariant function over a Riemannian symmetric space can be often expressed in the form of a determinant or a Pfaffian when you assume some additional structure on F. The long-term goal is to use these expressions as a bridge between Riemannian symmetric spaces and random matrix theory to study asymptotic properties of probability distributions on complicated sort of high-dimensional Riemannian symmetric spaces. And there's been a lot of interest in these types of questions. So there are 3 papers that basically came out at the same time, independently, that are looking at similar types of questions. And I think they were all the different works, one of which is ours, were probably inspired partly by Salem's earlier work on Riemannian Gaussians and how to use them for inference and the computational, get over the computational challenges that arise. So just to give some motivation and background, and given that this is GSI, it wouldn't be complete without some distinguished dead mathematicians. So the first question you might ask is, what is a Gaussian distribution? So I love this characterization, these various characterizations. So obviously a Gaussian distribution has a really illustrious and beautiful history. It was known for many years and used before even the 1800s, but really systematically and mathematically it was people started looking at it around the 1800s onwards. And one of the first people to look at it seriously was Gauss. And he showed that basically if you want a distribution for which maximum likelihood estimation of the mean reduces to an averaging problem, so a least squares problem, that basically ties your hand and gives you a Gaussian, what we call a Gaussian. Then shortly after, Laplace noticed the significance of Gauss's work and took it very far. So in particular in relation to the central limit theorem. So he basically showed that the distribution of the sum of a large number of independent, identically distributed random variables asymptotically converges to a distribution that is a Gaussian. So that's another way of characterizing it. Later on, Maxwell, in the context of kinetic theory, stumbled across the same distribution. He was interested in the velocity distribution of components of gases in in a box, and under some sensible physical assumptions, he basically again came out with the same distribution. Of course, it has close ties to diffusion processes, so it arises as the heat kernel, for instance, if you look at the heat equation. And more recently, following this sort of information theory development of the whole field, you can think of the Gaussian distribution as the probability distribution on the real line, which maximizes differential entropy among all distributions with fixed mean and variance. So here you see in many different ways, independently, the same thing pops up. Now, of course, this being GSI, we know that it's often important to work on manifolds. You have problems naturally defined on these various spaces. I won't go into the details to this audience. This is quite well known. But just this picture on the top just shows you in a very simple setting how a lot of these, so this is a robotic arm moving around, how a lot of these key spaces pop up even in a very simple setting. But this generalizes in many different contexts and dimensions and so on. Importantly, at least the first 4 bullet points there, these are Riemannian symmetric spaces. So these aren't just general manifolds, they're manifolds with a lot of symmetries in structure. Not to say that these are the only important manifolds. You have inhomogeneous manifolds popping up in other contexts as well. But you can go quite far, especially when the geometry is from the nature of the data itself rather than anything else. Okay, so now if you go back and say, okay, how should I define a Gaussian distribution on a manifold? Then you really have no right to assume that these equivalences stay. Once you have curvature, each one of these notions could give rise to a different density. And so Salem's work that goes back a couple of years is that he basically and colleagues looked at this first property and said, okay, I want a distribution where maximum likelihood estimation of the mean becomes least squares. And if you go with that property, you basically end up with what you might expect as the obvious choice of basically mimic the expression, the closed form expression with a metric and so on. Interestingly, this, I believe, also gives you the fifth one as well, the information theoretic, if you define the differential entropy and so on. The rest give rise to different distributions which are also studied closely. Probably the heat kernel approach actually dates back the furthest because people were looking at it in context of PDEs for a while. Now, if you want to do basic statistical inference, so this is like the simplest problem you might want to look at here, is you have independent samples drawn from some distribution and you want to estimate the parameters. So as we noted before, the maximum likelihood estimation of the mean becomes just a Riemannian center of mass computation, and the solution we know exists and is unique if M is non-positively curved. But then if you want to estimate the dispersion parameter sigma, then basically it's also doable uniquely because you can show that this log of z sigma is strictly convex as a function of this natural parameter. But the point is basically we need to know what the z of sigma is. So we need to compute this normalization factor for a lot of the most basic things you can imagine. And this also appears when you want to do Gaussian mixture model estimation with this stuff, or hidden Markov model, learning the parameters of hidden Markov models and so on. So this is a key quantity, and that's how we really started looking at these integrals. We wanted to compute the integral of exp. But then you might want to, compute all sorts of other integrals. But this was the original motivation. And so now I'll just touch on a bit of the geometry we need for the rest of the talk. So we're assuming that we are dealing with a Riemannian symmetric space, M, given by a symmetric pair G, K, with a Cartan decomposition given there, where G and K are sort of Lie algebras of G and K. A is a maximal abelian subspace of P, and delta is the set of positive roots on A. Now we also assume that G has this decomposition in the form of in terms of the center of G and a real Lie algebra that is semi-simple and non-compact, just GSS. Then the exponential map maps A isometrically onto a totally flat submanifold of M, and also crucially any X can be written as the form X is K X A. So you can think of K and A as like Riemannian polar coordinates in this setup. So it has a very nice sort of picture emerging. Now the dual of M is also known to be, given this setup, is a symmetric space with a symmetric pair UK, where U is a compact Lie group, and the Cartan decomposition is given by K plus IP, where I is just the imaginary number. And then the exponential map maps IA isometrically onto a torus, which is totally flat in M hat, and any X in M hat also has an expression in terms of like a polar coordinates K X IA. So that's kind of the basic background of the geometry. Now, if you assume F is a K invariant function, without ambiguity, we can then write f of x as f of a, where x is x of ka, if you will. So f really only depends on this a term. And then this result is sort of classical, and it comes from Helgeson's various books, that if you integrate f over m, you have this nice expression which involves an integral over a of f of a times this Schein mess, where lambda is a positive root of multiplicity m lambda, and dA is a Lebesgue measure on A. So this becomes an integral over a vector space now. So you've gone from a manifold, and usually you get a big reduction in the dimension of this. So this is already pretty good. And there's a similar result for the compact case. So you basically have a similar integral. The Scheins are now sines, and you now integrate with respect to the Haar measure on the torus. So this is sort of where this is the top result was what we were using to compute Z. But and then typically things like Monte Carlo computation of the integrals was the way this integral was computed, which actually became somewhat intractable when the dimension of say n by n matrices were going to 20 plus 50. It just was taking too long, and it wasn't very nice. And also, ideally, you want something in terms of sigma, because you don't just want a number. You kind of want the full curve, if you will, as the sigmas vary. So that's the Riemannian symmetric space machinery. Now touching on the random matrix theory connection. So for any positive measure, if you consider this z beta mu integral, where v is the Vandermonde determinant, and beta is 1, 2, 4 for reasons that should become somewhat clear, then these types of integrals have very nice expressions, sort of determinantal expressions, which are given here. So if n is even, you have Z1 of mu is the Pfaffian of some matrix Ij, where Mij has entries that are essentially these integrals over two-dimensional. I'll explain what a Pfaffian is if you haven't seen it before. There's a similar expression for n odd. And for any n for Z2 and Z4, we have determinants and determinantal and Pfaffian expressions for basically matrices with entries that are just 1D integrals. If you have a similar result basically on the unit circle. So if those integrals, this is like the compact dual picture. So you have the same business with the same kind of determinants of Pfaffian type expressions. And these are again classical from the random matrix literature. So you can see these types of expressions in key texts on the topic. So what is a Pfaffian if you haven't heard of it? I hadn't before working on this, or at least I didn't remember. So formally, for a 2n by 2n skew symmetric matrix A, you can define it as this thing. Basically, it collapses to 0 for any other type of matrix. For 2n by 2n skew symmetric, the square of the Pfaffian ends up being the determinant of the matrix. So there is this nice connection as well. But you can basically think of determinant as sum over all permutations and Pfaffians as sum over pairings if you look at the indices on A. But basically it's something like a determinant, or better actually, in terms of computation. Okay, so what is the main idea here? So if you add this additional hypothesis on f of A, that you can basically write it as the product of some positive function w of a single variable applied to each one of the components aj of this A vector in some orthonormal basis ej. So if you have such a nice sort of breakdown, then things become quite nice pretty quickly. The hope is then using this kind of symmetry, you can write all sorts of integrals of f over a Riemannian symmetric space as essentially some constant that you can work out, like pretty much in closed form, times one of these z beta mu type integrals. And those have connections to determinants of Pfaffian, so suddenly you get a very nice collapse of everything. So I will go through examples. So we kind of, as I said, we sort of noticed that, oh, a lot of these different integrals in spaces, you could write them in these very neat forms. I think the full general precise theorem and the full catalog will come probably in the next few months. But here I'll just go through some nice examples. So the first example is symmetric cones. So if you think of those Lie groups given on the top of this slide, M beta is then realized as a symmetric cone. Beta 1, 2, 4 corresponds to the cone of positive definite real, complex, and quaternionic matrices. If f is k invariant, k beta invariant, and f of x then has this sort of breakdown as a product of functions, some function that we have to find actually depending on f, even if it exists, then you can write the integral as some c tilde, which we have an expression for, times z beta mu. And then I should say the key here is finding the mu, right? The measure that makes this work. So the measure would be a function of w in general. So your f, you hope, has this breakdown in terms of some positive function w. Then you find a measure that is a function of this w. And then it seems like you can repackage things to get something in the form of a determinantal type expression. So here's an application. So if you go back to the problem I started out with, these were defined originally on SPD matrices and cones and so on, these Gaussian distributions. So we want to work this thing out. As I said, we were stuck with this middle type expression. So that AI minus AJ comes from the root structure. You don't need to so much worry about it. But basically, we were doing Monte Carlo on that, and that wasn't good for beyond 10, 20, 30 dimensions. But here you can see if you actually have used this measure given here, then you have the whole thing as a form in the form of z beta mu. So if you take, for instance, beta is 1, which is real SPDs, n is even, there's n is odd has a similar result. Basically, you have z as some constant that we know times a Pfaffian of some matrix whose entries are those 1D integrals, which actually here integrates analytically. So we have a closed form expression for z now. And the structure on f follows from x. I mean, that's encoded in the exponent, the Gauss. Okay, so that's the first thing. I should say, so this is a big improvement on Monte Carlo, but it's still, this isn't a free ride for the end, because actually computing these Pfaffians when m is like, the dimension is like 100 or something, is still kind of messy. Partly, we run into overflow issues and very small numbers. But anyway, it's a big improvement. And the hope isn't just that. The hope is even when computations can get tricky, because you have these closed forms, nice expressions, and these bridges with random matrix theory, you can do nice asymptotics on things. So, you can work out what the asymptotic distribution might be and so on. Okay, so then the next example, which is touched on the paper and will be spelled out later, is Grassmannians. So if you take these Lie groups now, M is a Riemannian symmetric space, M hat is the dual. The duals here are the real, complex, and quaternionic Grassmann manifolds. So these are p-dimensional subspaces of some field k to the p plus k. So I won't go into the details, but basically if you use the Helgason type expression and write it out using the root structures, which you have to look up and so on, you get kind of something messy. But the way we did it was kind of by eye. We sort of try to figure out what the right density should be to, and it works. So it seemed like, again, this is another example of something that so we can get all of this worked out. So the third and final example is classical domains. So here with these Lie groups, M are realized as classical domains. So these are elements of these things are complex matrices when beta is 1, 2. For beta is 4, we have 2n by 2n complex matrices. All of these have operator norm less than 1. And if beta is 1, you have some more structure, so they're symmetric, and beta is 4, they're anti-symmetric. But basically, that's the type of thing we're dealing with. If beta is 1 and 2, then X you can write as in that form. So there's a factorization in terms of K1, K2 unitary matrices, and the lambda is a real diagonal thing. So there is a natural factorization. There's more structure on K1 and K2 when beta is 1, and so on. But you get the idea. There are these nice factorizations depending on the parameters. Okay, so if f is k invariant and f of x has that sort of breakdown, then this integral using the root structures for this setup becomes that thing. The last two is a typo. It should be cosh minus cosh. This is the risk of making slides after the champagne reception. But if you do the substitution of uj as cosh 2 lambda and then use this particular density mu as w of a cosh blah blah blah, you see that again the thing breaks down. You can work out what the c coefficient is, and then so on and so forth. So the application here is also sort of similar as a toy example. So if you can define, so m is the Siegel disk is m2 in this picture. And you can have the same type of Gaussian distributions on Siegel domains. And so if you want to, again, work out the Z for the Siegel disk, you run through this thing and you see, it comes down to a nice determinant of something. And this is just a 1D expression that's quite straightforward to work out. So this is, again, a major improvement on any kind of Monte Carlo trick. OK, so I should wrap up. So again, just to summarize, we developed a bunch of determinantal expressions for integrals on symmetric spaces on a case-by-case basis through a non-exhaustive set of examples. So there are other symmetric spaces that we haven't covered, but these were very important ones that we looked at, and a lot of sort of functions would have the symmetries that we looked at. I mean, it seemed like a very strong condition, and it is, but if you have things like the Gaussian and you look at the Laplacian versions of it or other types of functions, those aren't crazy symmetries. Then we will sort of spell this out and make it either give an exhaustive list or prove it in a general way if possible. So the future directions is to use these connections as between random matrix theory and Riemannian symmetric spaces to study distributions on manifolds in general. So as an example, one goal of the program would be to understand the asymptotic properties of a joint distribution of that form and how that ties to the root structure. There must be some kind of nice interplay. And how in high dimensions, how these things work and asymptotics. And so hopefully you wouldn't have to, I mean, that's kind of the flavor of random matrix theory. It's sort of this magic emerges in high dimensions. And so that's kind of the idea. There's a bit of background, which is this chapter in this Handbook of Statistics book. And but again, these are early days, and we hope this will sort of develop into sort of more meaty papers to come. Thank you very much.